Day, welcome back to doing a little bit of work. The weekend was beautiful. Well, I'm filming this on Friday, and I know that the weekend's going to be beautiful, so I hope that it actually was, and you got outside and be able to do some things outside and enjoy the weather. So what we're going to do for this week's modules is just finish up unit number 4. Today I'm going to do a short little lesson on the driving forces, what actually makes a chemical reaction go to completion, or what makes a chemical reaction end up in an equilibrium, why that happens. And then on the Wednesday's module, you're going to be marking the driving forces assignment that you're going to do. Okay, so today's lesson is very short, and you're going to work away at the assignment. On Wednesday, you're going to correct the assignment. I'm going to post the solutions, and you're going to show me how you did, just so I can collect some evidence of learning. And then Friday, you're going to work away at just the review sample multiple choice test, and I'll put a little short quiz on Friday for you to complete sometime before the following week, and we'll get started at unit number 5. Okay, I hope everybody's doing well. I'm going to look at unit number 5 and just sort of see what we're going to fit in. I'm going to just work backwards from how many lessons I think we'll do. And then I'll map that out for you so you can see what the month of June is going to look like for us, and we'll just sort of see how many topics we can cover. Okay? All right, so for today what we're going to do is we're going to look at entropy. And we haven't watched a crash course lately. This one's actually quite funny. The concept of entropy is like chaos and disorder. And so I think the crash course is what you're going to want to watch first. So watch this. I'm just going to play the first little clip of it together, and then we're going to fill in the notes on page 35. Here we go.
Whether it's the terrible state of my office or the slow degradation of my body into dust, the universe tends toward disorder. But why? Why is the universe structured in this terrible and callous way? Well, it turns out it's not really the universe's fault. If you think about it, there's only one way, or at best maybe a few ways, for things to be arranged in an organized way. But there are nearly infinite other ways for those same things to be arranged. Simple rules of probability dictate that it's much more likely for stuff, whether it's the stuff on my desk or the particles and energy that make up my concept of self, to be in one of the many disorganized states than in one of the few organized states. It's simple math, and it's unavoidable. So unavoidable that it is, in fact, our second law of thermodynamics, which says that any spontaneous process increases the disorder or randomness of the universe. Processes that don't increase the disorder of the universe require work to be done in opposition to the disorder, and are in fact often impossible to achieve. The very act of putting one system in order requires that other systems become disordered. Think of it this way: your lunch was composed of an extremely ordered set of molecules.
Okay, I'm going to stop it right there. You can finish watching it. I forgot he went on and on for a little bit. There are other videos online if you want to watch a little bit more about entropy, but I'm just going to get going, and we're going to have a look at what we call these driving forces. Okay, so fill in with me if you can, and if you don't have a handout printed in, that's okay. You just make sure you summarize the 2 driving forces. This is what pushes a reaction to go in the way that you want it to go. Okay, so driving forces in a chemical reaction. Physical and chemical changes have a natural tendency to go towards or in the direction of these 2 driving forces. Think of them as the force that pushes a reaction to go in the forward direction, the reverse direction. There are 2 things that kind of make it want to go that way. The first is the easy one. It's minimum energy. We did energy in unit number 3. Do you remember the word for energy? And we're talking about heat, like a chemical equation. It's a thermochemical equation. Minimum enthalpy. Yes, enthalpy sounds like this new word called entropy, and this is where we look at the difference between them. So minimum enthalpy, so we're looking at our delta H. Therefore, which process is favored towards minimum entropy? Enthalpy negative, we're looking at an exothermic reaction. Okay, so that's one of the driving forces. It means that a reaction wants to go in the direction that is exothermic. Easy, okay? The second one, we're going to explain what this disorder talks about a little bit more, is maximum disorder, okay? Maximum, E-N-T-R-O-P-Y. Entropy, and the symbol for that is delta S. Okay, so I've summarized it over here. A tendency towards lower energy and a tendency towards increased disorder. When you have that, it means the reaction is going to go that way. Okay, so here are some processes down below in this table. So this table here shows all the ways where you can get increased disorder. Okay, more randomness. The disorder concept in physics and chemistry is a little bit hard to get at. There's a few other videos actually online. Professor Dave has one on entropy, and there's a TED Ed on entropy as well. It's a little complex, but let's just use some simple examples, and I think you'll be able to get it. Okay, physical chemical changes, you can have both types in order to describe the entropy. So these ones are all for entropy. Does it make sense that something in a liquid state is going to have more disorder than something in a solid state? So something that goes from a solid to a liquid is the format, the flow that shows increased entropy. And that should make sense, right? If you think of a solid, it's all contained. And once that solid starts to speed up and move faster and further apart as it changes state, clearly those particles are going to be more disordered. So going from a solid to a liquid, or going from a solid to a gas, any of these physical processes create a system that has more entropy, more disorder. Okay, so the examples on the handout here: melting ice, sodium reacting with water. Have a look. You've got solids, liquids going to aqueuses, and gases. Those states have more disorder. So here are some examples that increase the entropy of this system. Okay, does that make sense? Hopefully it does. The next couple, same with regards to change in state. Does it make sense that something that's got a liquid state is going to have less disorder, more order, than something that's in the gaseous state? Again, as those molecules move faster and further apart, they're more disordered. Okay, and we talk about that in terms of more entropy. Okay, next one: degassing of oxygen, hydrolysis of water. Those should make sense. The third example, dissolving. Again, if you're going from a solid state to an aqueous state, you're looking at a system where in the aqueous form, there's a lot more disorder than there is in the solid state. Okay, so dissolving, any of those processes, those ones are both physical changes. You've got more disorder. What about the number of gas molecules that you have on the reactant side or the product side? Okay, does it make sense that if you have more gas molecules, you're going to have more disorder because you're going to have more things that could be in different arrangements? So a system that has more molecules or more moles, if you're comparing a before and after, the one with more is the one that has more entropy. So have a look at the first one, combustion of ethane. Now, this is where I've just written down here, 4.5 versus 5. So if you've got 1, and I know this is one with just because you've got a fraction there, it's a little tricky, but you basically have 4.5 things on the reactant side, and you've got 1, 2, 3, 4, 5 things on the product side. The product side has more disorder because there are more gas particles. Decomposition of ammonia, can you see here? You've got 2 things on this side and 1 plus 3, 4 things on the product side. The decomposition of ammonia is favored because there's more entropy, there's more disorder. Okay, so then we just look at our examples that we've got. Can you predict if a reaction favors the forward direction? Is it going to go to completion? Is it going to favor the reverse reaction? Pretty difficult to want to go that way. Or is it going to be favored in both directions, where one driving force pushes it towards the reactants and the other driving force pushes it towards the products? Well, then you're going to get an equilibrium. And this is where everything sort of ties up nice and neatly. Here we go, we're done. So we have 3 examples, and there's 1 example for each. So here we go. You got to look at the lingo. The language that we use is the one you want to pick up on or summarize. If a reaction favors both driving forces, you remember the 2 driving forces? Minimum enthalpy and maximum entropy. Those are the terms you're going to use on the assignment on the next page. Okay, what are the two driving forces? Minimum enthalpy, maximum entropy. And if both of those are favored, they're both pushing the direction in the same way. Therefore, the reaction is going to proceed in the forward direction, and it's very likely to occur. So let's have a look at this equation. Complete combustion of propane. So I've written it as a thermochemical equation so we can see where the enthalpy or the heat is. In the forward direction, it is exothermic. That's one driving force. It pushes it in the exothermic way. And now the second one, we're looking at all gases. So let's compare the number of gas molecules you have on each side. I have 6 things on this side, 7 things on the product side. So clearly my entropy increases in the forward direction. And so this is a chemical reaction that is going to most likely get to completion. There's nothing that wants this reaction to go in the reverse way. Nothing about how the universe works says, oh, I want it to go this way. Nuh-uh. Both driving forces push it to completion, and it goes to completion. So we write the arrow that shows reactants to products. Easy peasy. Okay, let's look at the next one. What if the reaction has opposing driving forces? So what does that mean? It means that it would have to be minimum enthalpy and minimum entropy, or what if we had maximum enthalpy, so an endothermic direction, and maximum entropy? Then guess what? One driving force says, I want it to go this way. The other driving force says, I want it to go this way. You end up with an equilibrium. So you can predict pretty well using our knowledge of how reactions work to figure out if a system could reach equilibrium. Do we have an example of this? Yep, right here. Okay, production of ammonia from its elements. You can see that it is in the forward direction. It's exothermic. But what about entropy? Well, 1, 2, 3 versus 2. So you've got 4 moles on this side and 2 moles on this side. So in the forward direction, it's going at minimum entropy, minimum enthalpy, and guess what? Going the reverse, right? So you're going to reach a system that makes it to equilibrium. Last option, what if the reaction favors neither driving force? So that is in the maximum enthalpy. So is it the endothermic direction? And minimum, entropy, then the reaction is likely to not occur since the reverse reaction is favored. And do we have an example like this though, that actually happens, yet the universe says this shouldn't happen? Sure do. Photosynthesis, okay? It occurs, but how does it work if the universe doesn't want it to work? Well, we have things called chlorophyll molecules, we have loads of enzymes, and we have energy of the light from the sun that provides the energy of a photon to excite the electron. So does that reaction actually occur? Yeah. Okay, so it's not just magic, it'll actually occur. All right, so that's it for driving forces. So again, what are the two driving forces that make a reaction tend to want to go and happen? It's because of minimal enthalpy and maximum entropy. And if you have a system that favors the exothermic direction and it favors maximum entropy for any of the different ways that that can happen, you're going to have a system, chemical reaction, whether it's a physical change or a chemical change, it's going to actually work and go to completion. Okay, so that's it for driving forces and the concept, that last concept of entropy. So your homework is just to work away at this assignment. And again, I'm going to post a solution set on Wednesday. You correct it, self-assess it, show me that you've done it, and then we're going to do wrap it up on Friday for the short little quiz that I'll do. And that's it for this unit. I hope everybody's doing well. Okay, send me any questions via email if you've got any. Thanks, guys.